Hello, this is Mr. Gilmore with the 9.4, the tangent existence theorem and its converse. Now, we're seeing this word tangent already. We studied that with this understanding of this word tangent with our sine, cosine, and tangent functions. However, we're looking at another type of tangent today, which actually the two tangent words we've seen are going to be related in a future story that you will see. However, the tangent that we're about to unfold in our lesson today involves the existence of a line. And so we'll first actually talk about defining what a tangent line is, and then we'll move into proving that this tangent line actually exists, and then taking a look at its converse. So if a line and a circle are coplanar and they intersect at precisely one point, the line then is tangent to the circle. Now, that point that the circle and that line intersect at, we're going to call that the point of tangency. Essentially, imagine that this line and this circle, the only thing they have in common is one single point. And so in our diagram below, we have what we call line M, which we are going to call tangent to circle A, and B is the point of tangency, meaning that point B is both on the line and on the circle. Now, the real question that we have to ask ourselves is, do tangents exist? Is it even possible for there to be a line and a circle that are coplanar such that they are able to intersect at precisely one point? The thing is, definitions don't prove existence of this. For example, let me define a word called squazzin. All right, so this is a squazzin. If I define the word squazzin to be a positive integer whose square is 12, now that the definition is perfectly sound, the reasoning is fine. However, a squazzin doesn't exist, right? Because there is no positive integer such that we square that number, it equals 12. So just because we have defined something doesn't mean it actually exists. What we need to do is then prove that because we have defined this thing called a tangent line, let's actually prove that this thing, tangent line, actually exists. So let me introduce you to the tangent existence theorem. So they do exist. How do we know? We'll actually construct one. So here's what this construction is going to look like. We have a line that is perpendicular to a radius at its endpoint. So essentially, mark any point on a circle, connect the center of the circle to that given point, and then what we're going to do is produce a line through the end of the end point of the radius such that that line is perpendicular to our circle. And this construction, this theorem, this construction that we've actually just done, we're going to prove that this line is in fact going to intersect precisely at that one point B, which is then proving that tangents actually exist, known then as our tangents existence theorem, or to us the TET. So line M passes through point B, which is the end point of the radius, and the line M is perpendicular to AB, and we're going to prove then that M is in fact a tangent to the line, that it actually does intersect the circle at precisely one point. Now, the proof of this is a little bit subtle. Let's take a look at how we're going to actually prove that this line, M, intersects the circle at precisely one point, and it's just point B. So how do we prove it? We're going to prove this indirectly. Now, what we're going to do then is assume that M is not a tangent line, meaning that if we define a tangent line to intersect at precisely one point, that means if we were to then take take our assumption, which is to assume the negation of that, we would arrive that the tangent, this line that we've created, this line M, that intersects then at more than one point. So according then to our circle here, it would still have to pass through point B. However, it would also intersect our circle at point C as well. So now take a look at our diagram below. We are going to prove now that this is impossible. Let's begin first by remembering a few things about our circle. First thing is that whenever we have any given segment from the center of our circle to a point on the circle, which forms that radius, we know that all radii of any given circle are equal in measure. And that's actually going to help us as we dive into this assumption. All right, we've assumed that M is not a tangent line, which means we're going to find ourselves a contradiction. And we actually find the contradiction pretty quickly. Let's take a look at why. So let's prove that actually in this diagram below, that this triangle ABC can't exist. And here's how this triangle ABC can't exist. Since we have assumed that M is intersecting our circle now at 2 points, B and C, that means we've got actually two radii. AB is a radius and AC is a radius, which means we can call those two radii equal in measure. What type of triangle then do we have on our hands? We've got ourselves an isosceles triangle, which means that the measure of ACB, this angle here, is equal to the measure of angle ABC, right? Because of the isosceles triangle theorem. But do recall what was part of our given with the original construction of our line M. It was given such that M was constructed to be perpendicular to the segment AB, which means not only do we know that angle ABC is equal to angle ACB, but we know that angle ABC here is actually a right angle, which then makes angle ACB also a right angle. And now we have our contradiction, because the sum of all three angles inside that triangle would then be greater than the measure of 180 degrees, and that is impossible according to our triangle angle sum theorem. And so thanks to Tasty, we have ourselves our contradiction, which means we toss out our assumption, which, remember, the assumption was that M is not tangent, which means now we have proven by contradiction that M must be tangent. So thus we have our triangle existence theorem. Now, the tangent existence theorem. The tangent existence theorem actually does have a true converse as well. So now what we're going to be given is that the line M is tangent to a circle at a point of tangency B. Let's prove then that it is perpendicular to the radius constructed to that point of tangency. So in our diagram below, we have line M, which is a tangent, passing through the point of tangency B, and we are going to then construct a radius from our center of our circle to that point B, and what we're going to prove is that line M and our segment AB, which is our radius AB, are actually perpendicular to each other, that they will form right angles. So the proof of this as well, right, we're going to prove that this line actually is perpendicular to this radius at the point of tangency. The proof of this is also subtle. We are going to do this indirectly. So again, the proof is indirect, and what we're going to assume is that the radius isn't perpendicular to the tangent line, M. And what we know from chapter 5 is that if we don't have the line that is perpendicular, that means there must be a point on line M that would make AC perpendicular to line M, since point B is not that point by our assumption. So what we were saying is B is not the point that forms the perpendicular. Thus, there must exist a point that is not B. So let's choose a point C that is perpendicular then. That is the point AC, or sorry, the segment AC, which is perpendicular to line M. So based on our assumption then, we know that angle ACB here is a right angle. Now we are again going to arrive to a contradiction. Now this one takes a little bit more the behind the scenes to arrive at that contradiction, but we'll find that contradiction actually fairly quickly once we get to a point of showing where we have the this paradox going on. So the very first thing is, now that we have assumed AB is not perpendicular, that means AC is perpendicular. We've got ourselves a right triangle. ACB is a right triangle with right angle C. What does that mean about the length of the side opposite the right angle, which is the hypotenuse? What that means is it's longer than any of the two legs of the right triangle. In other words, AB becomes the hypotenuse, which AB is the radius. So by the right triangle inequality, this is something that we saw way back in chapter 5 as well, that we can actually prove that AB, which is the hypotenuse now, is greater than the length of AC. Now, we're going to find that there's going to be a contradiction here. Let's unfold that length AC and take a look at that one. See, AC, as we connect from A to C, it actually intersects our circle at another point here. And because it intersects our circle, let's call that point M. That means AC is actually divided up into two subsegments. We have AM and we have MC. But notice what AM is. AM is another radius, which means it must then be equal to that hypotenuse AB that we actually just discovered to be greater than our length of AC. However, AC is the whole segment, which means by our whole is greater than the part, we can claim that AC is greater than any of its two pieces or any of its two parts, which means it's also greater than AM. But what do we know about AM? AM is equal to AB by the definition of radius, which means another thing we just said is that AC is greater than AB. Now look at our statements here in 1 and our statements here in 2. those statements are contradictory to each other. AB is greater than AC and AC is greater than AB. That is impossible, which means we arrive to a contradiction such that this triangle ABC can't exist. And what we assumed was that AB was not perpendicular to our line M, but it turns out AB is perpendicular to our line M by the proof of contradiction. And so there we have it. We have both the tangent existence theorem and its converse to be true. I wish for you then to hop over and take a look at the 9.4 homework assignment on the TET and its converse. If you do have any questions on the homework assignment where you will be using these two theorems to justify several of the answers and also walking through the proofs of these theorems again, if you do have come across any questions on that assignment, please don't hesitate to email me. I will get back to you as soon as I can. With that, be good and do good.